All right, everybody. I think it's just about time to get started. People can keep trickling on in here. I wanted to make one quick announcement before I do get started. I'm going to be giving this same talk at Indie DevStock, which is another iOS developer conference in September in Nashville. Since that's a single-track conference, if you happen to be going to that one, you might want to check out one of the other awesome sessions that's going on right now. Otherwise, you're going to get stuck listening to me twice. Even I don't want to do that, but I don't have a choice. So, with that, let's go ahead and get started. So, over the course of this talk, we're going to be convincing ourselves that compilers aren't magic. Okay, sorry about that. Compilers aren't magic. All right, one more time here. Compilers aren't magic. Ooh, this one looks promising. I don't know where this is going. So sorry about that. I just had to get that out of my system. There will be no more GIFs during the rest of this talk. There will be, however, continued gratuitous use of skeuomorphic animations in Keynote. So buckle in for that. So over the course of this talk, we're going to convince ourselves that compilers aren't magic. Now, we're not going to live code a whole compiler right here, but what we will do is break the process of building a compiler up into smaller components, and any one of those components is going to seem manageable in and of itself. Now, some of those components, in fact, are going to be what I would call sufficiently stack overflowable problems, which is to say that they're kind of straightforward programming problems for which there are resources online that you could reference to make progress with those. Now, in some cases, we are going to see some techniques that are perhaps non-obvious, but are readily understandable once you examine them a little bit. So they're not magic, and you don't have to be a wizard to figure these things out. When we look at some of those topics, we're going to see a lot of Swift code. I'll put most of it right up here, I'll put a good amount of it right up here on the slides. And in particular, in a couple places, we're going to look at how some of Swift's little nicer features make our code even cleaner and nicer than it would be otherwise. So let's get started by asking a stupid question, which actually I found is a pretty good way to get started on a lot of different things. And that question is, what is a compiler? So when you ask a stupid question, you very often get a stupid answer. One such answer is that a compiler is a computer program. Now, that may sound obvious, but how often do we actually think about the fact that when we mash Command B in Xcode, what's actually happening is some other computer program is running and doing some work for us? This reminder actually tells us something important. All of us write apps, and apps are just computer programs, and those programs happen to run on little computers that are in our pockets. So we don't have to, there's no other prerequisites for getting started learning a compiler. You don't have to learn C++ or assembly. You just have to know enough to get a program to run on your computer, which all of us know how to do. So let's do that, and let's write a compiler in the tools that we're used to. We can use Swift as the language, and we can set up a command line application that's going to run right on our Mac. So we're writing an app, and that app just happens to be a compiler. The next stupid question we could ask is, what should our compiler do? We want it to compile stuff, obviously. But what does the process of what does that word fundamentally mean? Compilation, to compile something. So what a compiler really does is it takes source code in a language that the computer doesn't know how to execute in any way. And it transforms that source code into some other kind of code that one way or another the computer does know how to execute. So we call those things the source language and the target language, and the process that sits in between is the process of compilation. So now code, of course, we can think of as really just being a stream of characters. When we're in Xcode typing away, what we're doing is we're putting bytes in a file somewhere, and those bytes represent characters that hopefully conform to this language called Swift, and they give instructions in this language called Swift for processes that we want the computer to execute. But Swift is just an abstract concept, right? The computer doesn't know anything about that until the rubber meets the road with the compiler. So the compiler is what transforms our Swift code and the intentions that we have in it into something that can actually run on the computer. And that is the target language. Now that target language, which can be the assembly language of the specific processor where our program is ultimately going to run, but it doesn't have to be, at least not initially. I mean, you have to get there one way or the other eventually, but that doesn't have to be your direct compilation target. And in fact, the Swift compiler itself compiles to an intermediate representation called LLVM-IR. It's kind of like a low-level but general-purpose computing language. And that is subsequently compiled by its own toolchain down to the executable assembly that runs on our phones or our computers. So there are even compilers, real production compilers for languages that target higher-level languages like C. So they compile to C and then rely on a C compiler to get down to something that can run on the computer. And believe it or not, there are compilers that target interpreted languages, specifically JavaScript, and we do that so that we can compile code that can run directly in the browser. So what have we learned about our compiler just by thinking about it a little bit and generating some to-dos or some requirements for our app that we're going to build? Well, we know that we have to define a source language, some language that can express instructions to the computer, but which the computer doesn't currently know how to run. We know we have to choose a target language that we're going to emit equivalent code in. We're going to have to somehow read in a stream of that source language characters, and then we're going to break those characters into the components of our source language. We have to process those components to extract the instructions that the source language is presenting, and then generate equivalent instructions in the target language that can already run on the computer. And finally, we're going to have to write out that equivalent target language code and do some kind of finalization step, like maybe another intermediate build step. So let's get started by defining what our target language is, or our source language, excuse me. So one of the good things about writing your own compiler is that you get to decide what the language is. And since we're learning and getting started, we don't have to go straight to compiling something difficult like C. We can choose a very simple, straightforward language, and we can even design that language to make the process of learning about compilation easier. And that's what Bitsy is. So Bitsy is a language that aims to be the best language to target when writing your first compiler, or interpreter for that matter. And it's the language that I kind of created while I was learning about this stuff and while I was preparing for this talk. So there's a repo that I'll point you to here called Bitsy spec, and what that does, it's a command line utility that you can run against any implementation of Bitsy, and it includes a series of unit tests, and it will take your implementation of Bitsy and run the unit tests to let you know if you're following the spec of this little Bitsy language, or whether there's something that isn't quite right and you need to continue working on your implementation. So let's real quick take a look at what Bitsy is like. It's a very simple, very limited language. So Bitsy code goes always in one file, and in fact all of our executable code has to go between two keywords in that file, the begin keyword and the end keyword. And the end keyword is used to terminate other kinds of blocks in the language as well. So we have comments in Bitsy. They're block-style comments inside of curly braces, and those can go anywhere in the file. They can span multiple lines, but they can't be nested. So this is a little sample program that's calculating the factorial of a given integer, and it's a good thing that we chose to do that, because it turns out in Bitsy the only kind of data that you can process is integers. It's the only data type in the language. Variables in Bitsy can store integers, obviously, and they can be named with letters or underscores. Now, a lot of things in Bitsy look familiar in terms of assignment and math operators. Those are all the same that you're used to, the same precedence rules, infix operators that you see in most other languages like Swift. We also have a looping construct in Bitsy, so the loop keyword followed by an end keyword will repeat the block inside of it indefinitely until the break keyword is encountered. And the break keyword always exits the innermost loop, so loops are nestable. There are a couple different conditionals, or there are a few different conditionals in Bitsy, but they're a little different than we have in other languages. And that's because Bitsy, again, only has one type of data, and it's the integer. So there's no Booleans. That means we don't have Boolean logic or anything like that. We just have these conditionals if z. There's also if p and if n. So if z takes an expression, and it evaluates that expression, and if that expression evaluates to 0, then it executes the conditional code. There's also an optional else branch. And if p and if n work the same way, except for positive and negative expressions, respectively. So we have a little bit of I/O as well. We can read input in the form of an integer from standard out, and it gets loaded into the variable that follows the read keyword. And then we have a print statement that evaluates an expression and prints it out to standard out with a trailing new line. So that's it. That's the whole of Bitsy. It's obviously very limited and very small. The syntax kind of connotes that, right? It looks like basic and Pascal got in a car crash or something like that. And that's to let you know that this is a limited small language. It's not about building something particularly meaningful in and of itself, but instead learning about the process of language implementation. So we've defined a simple source language to target, and now we have to choose, or to implement, and now we have to choose a language to target. So this is the language that we're going to emit code in when we're compiling our bitseed. So if you remember when we talked about the target language, there was one requirement that we talked about, and that was that the computer has to know how to run it. But there's actually another requirement that's implicit in there, which is that we need to know how to write it, because our compiler is going to have to generate code in this language. So what's a language that the computer knows how to run and we all know how to write? Well, there's an obvious choice here, and it's Swift. So there may be some good reasons why Swift is not an ideal compilation target for a production real compiler, but it's a perfectly good choice to emit code in Swift for learning about the process of compilation. And if you later wanted to go back and learn assembly or LLVM and implement the code generation for that, then you could do that as well. So we've defined our source language, we've chosen our target language. Now we know we're going to have to read some characters representing that source from probably a file sitting on disk somewhere. So it turns out this is one of those sufficiently Stack Overflowable problems. We could figure out how to do that, and what we really want to do is just expose an interface for consuming or walking over that stream of source characters one character at a time. Now obviously during our compilation process, we're not going to want to be dealing at the level of individual characters the whole time. So what we have to do is break those characters into like the components of our bitseed language, and that is where the real meat of the compilation process gets started. So there's a fancy name for this. It's called tokenization. And what that means is that we just have to break our source code into meaningful chunks, which we call tokens. And then we have to return a traversable list of these tokens. So when you and I look at source code, like this example program in bitseed, we don't see it as just a stream of characters. We see it more like this. We group certain characters together and consider them as atomic units within the language. So we don't see a B, an E, a G, an I, and an N. We see the begin keyword, and we know that that means our source code for the rest of our program is starting now. And we do that with other keywords. We do that with variable names, right? And so we know that one variable name, a set of characters naming a variable, if used somewhere else, it represents the same variable. And comments, we know that we can ignore them in terms of the execution of the actual program. We break things up on looking at operators and integer literals, etc. So that's what we need to teach our compiler how to do. Let's start by defining those atomic units, those chunks, which we call tokens. And those tokens have to carry forward for the rest of the compilation process at least two pieces of information. The first is the kind of language element that we're dealing with. So if it's a keyword, if it's an integer literal, if it's a variable name, etc. And then it also has to carry forward the original characters from the source code that it now represents. So for example, if we were going to tokenize this simple bitseed program, perhaps the bitseed equivalent of hello world, what we would want our tokenizer to do is produce a stream of little data structures like this that carry forward this information. So for example, the first token is going to be the begin keyword. And then, for example, take a look at that integer token. What's important to note there is that the token not only says I'm an integer, but it carries forward the value of the integer, the 42. So obviously, if a bitseed developer puts 42 in her source code, and we're going to be creating equivalent source code in Swift, we're going to need to have that value. So we want to make sure that we carry it along with us. So how do we do that? Well, let's start by implementing the token. So we said that it had to carry forward the type of token that it is, and we'll do that with an enumerated type. We'll back that with a string, and we'll see why that's important in a little bit. And then we said we had to carry forward the raw value from our bitseed source code that this token represents. So it turns out there are two classes of tokens, and we need to look at how to implement each class. The first kind has one specific type, but can store arbitrary values. And the second kind has multiple types, but each type has a very specific value. So let's look at what we mean, starting with the first line. So an integer is an example of a token that has one type. It's always an integer, so we can just hard code that into our struct here. On the other hand, its value is arbitrary. It can be any string of digit characters. So we'll just leave that as a string, and we'll let Swift give us an initializer for free here. Now note that we're not validating that the value is in fact made of only digit characters. So we're going to have to do that somewhere else in our tokenization process. A variable would have an a variable token, I should say, would have an equivalent implementation. It's always a variable, and its string is arbitrary. So the second class of tokens that we had to talk about were the ones that have multiple types, but specific values. So keywords would be an example of this. Now our keyword implementation is a little bit more complicated, but not much. Think of an end keyword, for example. It's always represented in our Bitsy source by a capital E, a capital N, and a capital D. There's no difference between one end's token and another. But there are many more tokens, or not many more, but a number more tokens than just the end keyword. So remember, we backed our enumerated type with this raw value, and it turns out that raw value is the literal string that is always going to represent this particular type of token in our Bitsy source code. This is just a little nicety that Swift gives us. So our keyword implementation can now take a string, and it can attempt to create a token type using that as the raw value. And if that succeeds, well, we must have a keyword. And if it fails, there's really not much we can do here, because the string that you're handing us simply doesn't represent a keyword in our language. So we use a failable initializer, and we return nil in this case. Now, in addition to keywords, operators, and parenthesis tokens have an equivalent implementation, because they also have a fixed string, which always represents them in the language. So we've now taken a look at we've now taken a look at how we implement the individual tokens. Now we need to implement the tokenizer. And the tokenizer is the process that needs to walk over that stream of source characters and return a stream of tokens. So the public interface just exposes the ability to peek at the current token and advance to the next token. Now internally, our advanced method is just going to use this takeNext method, and that takeNext method is going to do exactly what it sounds like. It's going to walk over our characters and take the next token and set it to our current token. So the implementation of that takeNext function is really the meat of the tokenization process. So let's think about how we would tokenize an integer literal like 42. If we were looking at this 4 character, what we would want our tokenizer to do is recognize that the 2 character belongs concatenated with it, and return an integer token with the value 42. So how might we implement that? Well, if we formalize that rule, we would say if the current character is numerical, take all subsequent numerical characters and create an integer token. So here's an implementation of that using a switch statement in Swift. And we switch on the current character in our code stream. And we do this funny thing. We say case is number. And then in that case, we take all the subsequent characters matching his number, create a string with them, and then create a token with that string. So what is this isNumber thing? It's not something that's built into Swift. IsNumber is just a function that takes a character and returns true or false based on whether that is a digit character. And the reason I'm able to use it here in this case statement is because I've implemented this custom pattern matching operator, which just tells Swift that I want to enable pattern matching on characters. You can do this with your own types, and it can get significantly more complex. And it's a pretty, I think, underrated feature of Swift that can help clean up your code. So this is an implementation of a tokenizer that can handle just integers. Oh, thank you, Swift. Let's expand it to handle tokenizing whitespace. So in this case, we add another statement or another case to our switch statement, and we say case is whitespace. And here I'm showing you the is whitespace function. There's nothing particularly special about it. But again, because we already overloaded that pattern matching operator, we can use it directly in our switch statement. And I'm also using it in another place. I'm passing it as an argument into my takeMatching function. This is another little nicety of Swift that we can use functions as first-class citizens. So that takeMatching function just generalizes the process of taking the next n characters in our code stream that conform to this function's definition of matching, and concatenating them together and returning that string. So again, just helps us clean our code up and keep things kind of simple and easy to read. So now, those were a couple of easy cases because we could always look at the current character and know what kind of token we needed to create. It gets a little bit more complicated when we deal with this case of having to disambiguate variables from keywords. So in Bitsy, this all caps loop counter, that's a perfectly valid variable name, and we could do something like assign 10 to it. But if we encountered that in our source code, and we're trying to tokenize it, we wouldn't know until we got all the way to the C character, or past the P character, whether we were dealing with a variable name or a keyword. So we have to somehow disambiguate between these two. Now we could think about implementing something that kept looking ahead at characters until it could gain enough context to figure out which you were dealing with. But it turns out Swift makes this even easier because the some of the choices we made earlier. We can define something as an identifier if it is composed of letters or underscores. And in that case, we can take a string matching the identifier and try to create a keyword with it. And because we use that failable initializer that's backed by the raw value in our enumerated type, if this succeeds, then we know we have a keyword, and if it fails, we can assume that we have a variable. So a pretty clean, simple implementation of dealing with this problem. So we've implemented a tokenizer that can handle whitespace and integers and keywords and variables. We've gotten pretty far. There's a few things left, but it turns out those things are really straightforward, even easier than what we've seen so far. So parens and operators are single character tokens. If you have that character, just make a token with it, and you're done. Comments are easy as well. If the current character is an open curly brace, take all the subsequent characters you encounter until you get to a closed curly brace, create a token with those. So we've now implemented tokens for all the elements in our source language. The next step now is to move on to actually processing those tokens and as instructions from the developer, so in our source language. So there's a fancy name for that process. It's called parsing. And what we want our parser to do is to succeed if the program is valid and fail with an error to the user if the program is invalid. So our tokenizer just breaks things up into tokens, but you could write a bunch of nonsense that are all valid tokens but don't express meaning or a meaningful program in the source language. So our parser needs to deal with this problem. For example, let's talk about how we would write something that could parse the simplest program in Bitsy, the Bitsy null program. It's just the begin keyword and the end keyword, but it doesn't do anything, but it is valid, and so we should be able to parse it, and we should be able to compile it. But it's not quite as simple as it looks, because those two keywords are separated by whitespace, and that whitespace is arbitrary. So we have to think about how we're going to deal with this. And to do that, I want to introduce just a little bit of formal notation. So we're going to say that our program is the valid inputs to our program are defined as being equal to the begin keyword, followed by a whitespace character, followed by 0 or more additional whitespace characters, which we just notate with those curly braces, followed by the end keyword. So once we define that, there's a name for this. It's called the grammar. And again, it's just the definition of the set of valid programs that our compiler can handle. So once we've defined our grammar, how do we parse it? So here's a very hard-coded implementation of a parser that can handle this very simple limited grammar. What we do is we use guard statements that's set, and we guard to say, does the current token's type, does it match begin? And if it's a begin token, then we're good and we can continue. But if it's not, we want to throw an error out to the user, telling them that we are expecting a begin token but got something else. If we succeed, then we advance at least once, expecting a whitespace character, and subsequently advance past all other whitespace tokens that we might encounter. Then we use another guard statement to ensure that the final token we encounter is an end token, again throwing an error if it's not. So this is very hard-coded, obviously, and it's very simple and straightforward, but we can already see something important about how parsing works, which is that the shape of our parsing code follows the shape of our notation. And that's why I introduced this notation, not just for an academic exercise, but because it's actually useful in helping us determine what the implementation of our parser looks like. And I think that's a little bit more obvious if we refactor our parser a little bit. So let's do that. So here's the parse function where we've extracted what those guard statements were doing into a match token type function. So this will throw an error and cease compilation if it doesn't get the token type that you pass in. And the advanced token function also helps us here to advance automatically past any number of whitespace tokens or comment tokens. So you can see clearly how this matches the shape of our very limited and simple notation here for our simple grammar. We can actually go a little further. We can move that advanced token call into our match function, because anytime we match a token, we're going to want to move on to the next one to process the next token. And we can then remove them from our notation, those whitespace characters, since we're not really having to think about it anymore. We're skipping past those automatically. They separate tokens, but they don't have any meaning toward the execution of our program. And we can even go one step further and extract a program parsing routine into its own function. And so now our notation and our implementation are very clearly aligned. So this is good. We've implemented a grammar that can handle the simplest Bitsy program, the Bitsy null program, but we want to go a little further. We know that in a real Bitsy program, between the begin and the end keyword, there's going to be any number, any sequence of valid bitsy statements. And so we're going to call that something. We're going to call it a block. So a block is any sequence of valid bitsy statements, but let's start by implementing just one, which we'll start with the loop statement. So we define our block as being 0 or more loop statements, which we, again, notate with those curly braces. And then we define our loop statement as being the loop keyword, followed by any number of valid bitsy statements, followed by the end keyword. But we already said that any number of valid bitsy statements is called a block. And so we just use that in our notation. We say that a loop is the loop keyword, a block, and the end keyword. So something interesting has happened here. Our grammar has become mutually recursive. Blocks can have loops, and loops have a block inside of them. So we can handle the bitsy mill program. This still works. Our grammar also defines programs with a single loop statement or many loop statements one after the other. But most interestingly, it handles nested loop statements, arbitrarily nested loop statements. So implementing a recursive grammar like this, there's a name for the algorithm that you use to do it, and it's called recursive descent. Again, another one of these fancy names, but the process is pretty straightforward. So let's look at that now. Here's our grammar. Again, just repeating that, and here's where we left off with our parsing, our program parser. So since we see that we've added the block in between our begin and our end keyword, all we'll do in our parser is call out to a block parsing routine, which we'll just define as another function. Now a block can have 0 or more loops, and if a block is terminated with the end keyword, so what our block parsing routine will do is keep on parsing loops until it sees the end keyword. And now our loop parsing function will match the loop keyword, parse a block, and match the end keyword. So this is a complete implementation of a recursive descent parser for the simple grammar that we see above right here, this little subset of our small language. We want to expand it, so let's add the break keyword into our language. And now we can say that a block is defined as 0 or more loop or break statements, and a break statement is just defined as the break keyword. So now instead of our block parsing routine, instead of just assuming we always have loops, we'll look at the current token, and we'll say, if the current token is a loop, then go parse a loop, and we'll dispatch to parse a loop. And if the current token is not a loop, well, the only other valid statement in our language right now is the break statement, so then we'll go parse a break statement. And our break parsing function is really simple. And it's interesting here that I had to name our break parsing function doBreak instead of just break. It's kind of a happy accident because we bumped upon a limitation of Swift, so break is a reserved keyword in Swift as well. And having just implemented a tokenizer, we can kind of understand why that is the case in Swift. Imagine if in Bitsy, for example, the loop keyword could also be used as a variable. And remember how we implemented our tokenizer to disambiguate between a variable and a keyword? Imagine how much more complex that would be if we had to figure out the context of that loop keyword to determine whether or not it was actually a keyword or a variable. It would add a ton of complexity, and so we don't allow it in Bitsy. And similarly, in Swift, they don't let you use certain keywords in certain instances. Now we understand why. So we've implemented a parser that can handle this subset of our Bitsy language, but we haven't actually done anything other than ensure that the developer has given us a valid program. So if it's valid, we'll succeed, and if it's not, we'll give them an error, but we're not creating anything that can run on the machine. So that's the next step in our compilation process, and it's called code generation. And this is where we want to produce code in the target language that has the same effects as those expressed in the source language. So how could we think about doing this? Well, it turns out you can start by just doing it right in line with parsing. So we'll actually just print out for now code that matches the semantics of the keywords that we're processing in our source language out into our target language. So what does that look like? Well, we know in Bitsy, if you have a loop keyword, what you're saying is, I want the subsequent block to be repeated indefinitely. So how would you express that equivalent of that in Swift? Well, you could use a while true loop to do that. So after we match a loop keyword, we're going to output that equivalent code in Swift. And like I said, right now we're just using print statements. Then we go parse a block, and we assume that the block parsing is outputting its own code for whatever that block is doing. And then when we match our end token, we know, because of the way we implemented this, we want to then close our loop. So we want to use a close curly brace. And we could do the same thing with our break function, and since the semantics of break in Swift match the semantics of break in Bitsy, this is really easy. We just output the break keyword. So this is really all there is to it in terms of code generation. It does get more complicated, as I'll show later, but for this simple case, this works. And to kind of demonstrate how this is working, because it does almost seem a little magical, I want to step through, or show an animation that steps through the parsing of this simple Bitsy program. Now this program doesn't do anything, it's useless, but it is valid, and so we should be able to parse it and compile equally useless and equivalent Swift code. So that's what we want to see if we can do. And what we're going to do is on the left-hand side, we'll build up the program or the stack of our compiler as it's executing, as it's processing this code. This is going to be our program stack. And then the blue arrow is going to indicate what token that we're parsing right now. And on the right-hand side, I'm going to show what code has been generated. So buckle up, this is going to go quick. So I don't expect you to follow this 100%, but what you should see is that as we go deeper, as we nest deeper into our source code, the recursive descent parser just keeps dispatching out to more parsing functions. So every time we hit a block, it dispatches out to parse whatever statements are in that block. Here the block is going to build back up the stack to parse our break keyword. And finally we return all the way to our outer loop, match the last end token, and then return to that block that represented our whole program, and we're done. And along the way, we output this Swift code on the right-hand side, and we see that Swift code is exactly equivalent semantically to the Bitsy code that we were parsing. So we've succeeded. We've parsed and generated code. We've compiled this simple program. Now, I have a confession to make here, which is that I did show you the simplest case possible. In fact, the loop statement in Bitsy was specifically designed to be really straightforward, really simple to parse and generate code for. And as you go forward and have to parse more complex statements in the language, or any language, it does get more complicated. Now, we don't have time to talk about exactly how it does that, or to implement any of them together right here, but what I will point out is that there's a couple things to recognize. One is that things get less literal and more mechanistic, right? So the code that you're outputting doesn't have to be a straight translation. It just has to have the same effects as the code that you're reading. So, for example, a straight translation of this assignment statement in Bitsy, if you were to straight translate that into Swift, you would say something like var counter equals 10, right? Really straightforward. Well, in the process of parsing this statement, you're not going to be able to do it that easily. So you have to think of a way to create these same effects with your code, basically. The other thing to note is that we didn't have to do this when parsing the loop statement, but obviously when parsing something like an integer literal or a variable name, you're going to have to use the token value, the value of that element in the source code somewhere in your generated source as well. So let's look at what our generated code might look like for this assignment statement. So we have a stack somewhere that we're going to append or push a value on, like the value 10 that we parsed out of our source code. And then we're going to have a temporary variable that we call register, and we're going to pop that value off the stack and put it in the register. And then we'll have a variables dictionary, and the counter element, the element at the counter key in our variables dictionary, gets set equal to whatever we just loaded into our register. And since we're using these temporary variables, we have to initialize them somewhere in our generated Swift code. So we can do that, for example, when we parse our begin keyword and put them into our code at that point. So the point here is, obviously, things get more mechanistic and more complicated, but hopefully you can imagine this as being a more complex set of a problem you've already seen solved in a simpler case. So it's a programming challenge, but it's not magic, right? It's something that if you played around with it, you could figure out how to do. Here's another example where we would just be decrementing that counter. I won't go into this code, but again, the same lessons here are the important ones. That we're using like temporary variables, but at the end of the day, the results are equivalent. The effects are equivalent in our generated code. So there are some remaining things to handle in the process of parsing and code gen. So obviously we wouldn't just want to use print statements. We would want to generalize and extract that process and do something that would allow us to output it to a file somewhere. We're going to have to parse more complex statements, like I said. So, for example, handling conditionals, where there's 3 conditionals with very similar semantics but slightly different implementations. How would you handle that? How would you handle the optional else statement? This is something I really wanted to talk about, defining a grammar that handles operator precedence. there are some actually good resources for figuring that out, and I wanted to talk about it, but it just didn't fit. And then even in our little language like Bitsy, we have some undefined behavior. So for example, what happens if a break keyword exists outside of a loop statement? We didn't define that. So somehow our implementation would have to handle that. So again, hopefully you can imagine these things as kind of programming and challenges that you could imagine tackling, rather than something that is mysterious and reserved for only the prized few who understand compilers. So we've gotten pretty far through our to-do list. The last thing to do is, again, to write that Swift source code out to a file somewhere and then shell out to Swift-C to produce a binary that can actually run on our computer. So this is another one of these Stack Overflow problems. And with that, we've really gone through the entire process of writing a small, simple compiler. Now, if you're interested in learning more, I'm going to humbly suggest a couple of repositories. So I already talked about Bitsy spec. That's that set of unit tests that you can run against your own implementation of Bitsy. You could even TDD an implementation of a compiler or an interpreter for the language if you were interested in that. Bitsy Swift is the completed implementation of the compiler from which I took all the code samples that I showed today. So if you want to check that out, I also, just this morning, added a bunch of header doc comments that add some explanations and some of the content that you saw in the talk right in line with the code as well. So hopefully that's a good resource. One other thing that I'll point out is this paper called Let's Build a Compiler, written by this guy named Jack Crenshaw back in the 80s. It's really, really, really good in that it's very practical. Unfortunately, a lot of resources for learning about this stuff start with a lot of theory and are very opaque. And this paper I found was very approachable and practical right from the beginning. And for me, when I started trying to play around with this stuff just on the side as a hobby, this was the paper that started to actually click for me what was going on. The other thing I'll mention is that either of those two repositories have a resources section in their README that call out a handful of other resources that I think are good places to start. Also going to just shamelessly ask that if you enjoyed this talk or are interested in learning about this stuff, GitHub stars really do help discoverability. I'm hoping that this little Bitsy language will actually help other people who are thinking about language implementation have a place to start and learn from. And so GitHub stars are welcome. So that's it, and I think we may have a few minutes for questions. If you don't get to ask a question, you can always find me at any of these places on the internet, or come talk to me at the rest of the conference. Thank you.